Hey, AP Chemisters, this is Mrs. Vanderlei bringing you Blankwalle 510. Hey, this is the last section of Chapter 5. Woohoo! This is about real gases. Up until now, we've been pretty much talking about perfect, ideal gases, but there is no such thing as the perfect gas. Reality sets in, okay? So, what are some factors that will attribute for gases to become less and less ideal, okay? And if it's less and less ideal, Pivner isn't going to be enough, okay? So it says most gases behave ideally until you reach high pressure and low temperature. It says, by the way, either of these can cause a gas to liquefy as a go figure. So if it's so less ideal, it becomes a liquid. Well, there you go. So there are two things that we can talk about. The first one is the idea of volume. So why does pressure have to do with it? Pressure has a couple things going for it. So here's my container, all right, at 1. So if I put a lot of pressure on it, what happens to this volume? The volume gets squeezed in. So our assumption that the volume of the gas molecule is practically zero becomes less and less true, okay, because the distance apart from one another is shrinking. So then the size of the molecule does become significant. So it says for gases at normal temperatures and pressures, all right, this is true, okay? But at high pressures, again, the volume of the gases then occupies a significant portion of the total gas volume, and no longer is that size negligible. Johann van der Waal, my hero, modified the ideal gas law to accommodate this. So you notice we're talking about volume, so we divided both sides by P, so now we have nRT over P, and here is this correction factor. So N is the number of moles, and then B is a correction constant that depends on which gas is being used. You have to look that up, okay? You will not have to do this for the AP exam, I promise you. Well, I shouldn't make promises I can't keep. I'm pretty sure, though, okay? So that's one. The more important one, the one that I think that will probably show up on the AP more likely anyway, is the effect of the intermolecular force. We will talk at great length about the intermolecular forces later on in AP. We did talk about this in first year chemistry, by the way, okay? It was your chapter 6. You probably don't remember that. But what is an intermolecular force? This is the idea of attraction, okay? So what is the effect of attraction? So first of all, the KMT assumed there was no attraction. There is no Harrison Ford coming into your container. But is that necessarily true? And it all depends. So if you have normal temperature and pressure, yes, you can have attractiveness just by the nature of that molecule. So if a gas is polar, what does that mean? Unequal distribution of charges. Then there's an attractive force between them. What I call the big four, and you're going to hear about what I call the big four. You won't see that in the book. This is just a Mrs. Vanderwalleism. Are your nitrogen, oxygen, fluorine, and chlorine. Notice my examples have oxygen, nitrogen, fluorine, and chlorine. So why are they the big four? They're the most electronegative elements that that exist, okay? And because of those high electronegativities, they become polar. So I put a picture. The picture is not in your notes, but this is a picture of your water. And notice that water has a partial negative and a partial positive end. The oxygen being highly electronegative is your partial negative, and the hydrogens being paired up with this highly electronegative oxygen are partial positive. So notice these little lines. You go from the negative oxygen to an attractive partial positive of your hydrogen. And notice how all those little lines are working. It's always between the red oxygen and the gray hydrogen. No two oxygens are going to be paired up, and no hydrogen ends are going to be paired up, okay? Because they will repel each other if anything. So that is the effect of a polar molecule of having that attraction. So this is true under any circumstance, whether it's high pressure or normal pressure, whether it's normal temperature or low temperature, okay? So what happens for the rest of the molecules at these extreme temperatures and pressures? Well, if it's under high pressure, then the molecules are squeezed together. There's a greater probability of collisions, therefore a greater probability of attraction. Think of this, homecoming. Crowded dance floor. You are dancing away, but it's so crowded. Keep bumping into people, okay? The more collisions, the more bumping into people you have, the higher probability that an attraction is going to occur. Now that's using kind of just an analogy. Why is there in the real world of gases, why is that the case? It's because as these molecules get closer and closer, you're going to have a better chance of having an interaction between the electrons of one gas molecule and the protons in the nucleus of another gas molecule. So if you can get them close together, then those attractions can occur. Same thing with temperature. At low temperatures, they're going very, very, very slowly. So when a collision occurs at these slow rates, all right, they're barely moving past each other, again, there's a greater probability of attraction, okay? So your conclusion is if an intermolecular attraction exists, meaning if it's polar or not, the collision would be considered inelastic, or they're not inelastic, meaning they are elastic, okay? So what does that mean? The van der Waals will account for this, where you have P equals nRT over V, and then you have this ANV squared stuff, and this is a correction. So you do not have to worry about doing problems like this on the AP. I don't think they've ever asked you to actually calculate this, okay? The van der Waal equation, Johann van der Waal came up with this, lucky us. Corrects for this negligible volume and for the collisions leading to the intermolecular forces. This is his real claim to fame and Mrs. van der Waals. You know what? I'm reading this. So if the intermolecular attractions exist, collisions are inelastic. Get rid of that not. They are inelastic, so they do lose energy. Okay, because you have to pull them apart because of that attraction, like pulling apart two magnets. So cross out the word not. All right, so it says A and B are van der Waal constants. Again, you don't need to work out the problems. It's the concepts that are important. So note the pressure is increased because it's P plus this quantity. Why is it increased? Because you are correcting for this intermolecular forces at lower pressure. Volume is decreased. Why? Because it's correcting the container to a smaller, quote, free volume. What does that mean? Free volume means without the volume of the gas molecules there. Okay, so let's see what the next page is. Okay, these graphs are pretty important. The AP loves showing you graphs and making you decide what's going on here. So let's take a look at this. Your y-axis is PV over nRT. Think about that. If I use PV equals nRT, divide both sides by RT, isn't that quantity equal to 1? So the closer it is to 1, the closer it is to being a perfectly ideal gas. So that's your y-axis. Down here is pressure. So I actually have three things going here. I have this how ideal it is. The closer it is to 1, the more ideal. I am changing the pressure, and what else am I changing? I'm changing the type of gas. If I'm changing the type of gas, then I'm looking at perhaps what molar mass is, okay? So it says when PV divided by nRT equals 1, the gas ideal. All of these are at 200 Kelvin, so I'm not changing the temperature, so it's a pretty cold temperature. It says note where the pressures cross the curves, where the curves cross the dashed line is where ideal. So where is all of them ideal at? Well, 0. Well, okay, we can't be ideal, but pretty close. And then hydrogen will never go back to being ideal. It just keeps going there, you know, going up. The other ones kind of dip down and then come back. So they can be ideal at different temperatures. I'm sorry, different pressures too. But what's the overall look at this? So each gas, after a certain pressure, after pressure keeps going up, okay, then it becomes less and less ideal, okay? So here at the beginning, at really, really low pressures, they are not very ideal, all right? I guess low is relative, I guess. You know, here's 1 atmosphere over here. That's pretty low. But as pressure goes up, all right, you go less ideal, and then notice how you're going past the perfect ideal gas to really not ideal anymore. That's what high pressure, they're being squeezed together. Those collisions are causing attraction, making them less and less ideal. Over on the second graph, what's going on here? Notice we're just looking at nitrogen, no other gases, just nitrogen. So again, we are increasing pressure, but notice we have 3 different temperatures. Which temperature is least ideal? That's your really low temperature. Why? Because the molecules are moving slowly. And if there's a collision, then they can have that attraction again, okay? There is time for that attraction to occur if they're moving that slowly. Notice the red line is where the gas molecules are going the fastest. And when they're going so fast, they're going zoom, 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 zoom. There is not a lot of time for that attraction to occur. So they behave more ideally at high temperatures, if you look at it, than the low temperatures. Okay. So it says, number 38, explain, whoa, sorry about that, explain why gases behave less ideally. So there's a certain phraseology you really need to kind of nail down here. If they're closer together, you get more collisions. You have a greater chance for attraction, okay? Again, go back to that idea of homecoming or prom or something where you have all these people on the dance floor and you're really, really crowded. The more collisions, the more that spark can occur, greater attraction. What about why low pressure? Why do they behave ideally? Well, they're far apart. At low pressure, volume is high. You're going to have fewer collisions and fewer opportunities for that attraction to occur. So problem number 40, which would you expect to have behave less ideally and why? We'll look at these two. I see one of those oxygens there. Remember what I said about nitrogen, oxygen, fluorine, and chlorine? Those are your polar molecules, or highly electronegative elements that you will have attraction. Neon is a noble gas, and what do we know about that? They're pretty much ideal as it is. Now, what about down here, helium versus xenon? Which is going to behave less ideally? Well, it's going to end up being xenon, okay? Why is that? It has a greater molar mass. So if it has a greater molar mass, it's going to move more slowly, right? Now we talked about that before. So if it moves more slowly, then it has a greater chance for that attraction to occur. So it's going to behave less ideally. Helium is one of the lightest gases besides hydrogen. It's going to go so fast, has very little opportunity to have that attraction with another helium. Okay, so problem number 41, well, you know what? Let's not do it. You're never going to be asked to do it as far as the AP goes. So let's just quit here. And that's the end of chapter 5. Be ready for questions. And as always, don't wait to be great. See you next time. Bye-bye.